All right, we're in section 2.4 today. We're talking about the product and quotient rules. Both of these rules are additional differentiation rules, which means rules for taking derivatives of certain types of functions. We went through a whole lot of different differentiation rules and techniques in the previous section, and this is basically going to be like adding to that list. So the last section, when you look at all of those different techniques that we covered, that gives us efficient methods for finding the derivatives of a whole lot of different types of functions. But there are still several functions that we cannot take the derivatives of just using those techniques. One example is right here. F of x equals x squared times the natural log of x. There is no way to algebraically simplify this in any way that would make any of those previously discussed differentiation rules usable for this function. Yet, this is a function that could arise in some kind of application, and we may need to take a derivative of it somehow. So the thing that we want to recognize with a function like this is that it's a product of one function of x with another function of x squared times natural log of x. By themselves, each of those functions, whether it's x squared or natural log of x, are easy to take derivatives of now that we have rules for those. We would use the power rule for this one, and we know that the natural log of x has a derivative of 1 over x. So how do we then find the derivative of a product of these two functions? Well, it's tempting, kind of, if we look at the sum and difference rules that we looked at in the previous section, it's tempting to think that if you want to take the derivative of a product of two functions, that it's just the product of their derivatives. So in other words, the derivative of f of x times g of x is just f prime of x times g prime of x. But this turns out to actually be false, even though it feels like it should be true. And it's very easy to show why it's false. We can use an example. So for example, consider this function right here. Y equals x to the fifth power. Now we know how to take the derivative of that because it's a power function. So using the power rule from section 2.3, we know that y prime would be 5x to the fourth. That's a super straightforward derivative to take, and we have done those plenty of times by now. But let's just say that alternatively we chose to take the expression x to the fifth power and rewrite it as a product of two functions, x cubed times x squared. This is the exact same thing as x to the fifth. So if I take the derivative of this product, I should get the same thing as if I took the derivative of x to the fifth, since they are the same function. If this technique actually worked, let's see what would happen by taking the derivative of this right-hand side. So if I wanted to take the derivative of x cubed times x squared using a technique like this, then I would be taking the derivative of x cubed and the derivative of x squared separately and then multiplying those together. From our power rule, x cubed has a derivative of 3x squared has a derivative of 2x, and multiplying these together would give me 6x cubed. Notice I did not get the same thing that I got here. But if this rule worked, then these should have been the same. So that shows right away that this is not how you take the derivative of products of functions. How do you take the derivative of products of functions? Well, we use what's called the product rule. If I want to take the derivative of f of x times g of x, it's equal to f times the derivative of g plus g times the derivative of f. You can also write that in prime notation, so f times g prime plus g times f prime. That's the product rule. That is how we take derivatives of products. And it's not what you would have expected, but it's the thing that works. It's very common when we're introducing the product and the quotient rule, which we'll talk about later in this section, to represent it using variable notation instead of function notation. So it's not uncommon to set a variable like u equal to f of x and a variable like v equal to g of x so that we could rewrite this rule this way. The derivative of uv is equal to uv prime plus vu prime. Okay, so notice each product has one of the original functions as a factor, and then the other function's derivative as the other factor. And we have a term for each of those possible combinations there. So going back to our previous example, let's verify that this rule works with the way that we broke down x to the fifth. So if I break x to the fifth down into x cubed times x squared, and then I set u equal to x squared and u equal to x cubed and v equal to x squared, kind of like what we were suggesting here, then u prime would be 3x squared, which we see here. V prime would be 2x, which we see here. Those are just from the power rule that we already know about. So if I use the product rule, then the derivative of this product of functions, x cubed times x squared, should be u v prime plus v u prime. And you can see where each of those things are in these parentheses here. We had already written them out here, so I'm just putting them where they belong in the product rule. When you multiply things and simplify, x cubed times 2x is 2x to the fourth, x squared times 3x squared is 3x to the fourth, and when I add these together, I get 5x to the fourth. But that is what we needed to get, because that is, as we already know, the derivative of x to the fifth power. Okay, now this is not, the point of showing you this is to not give you another way of finding the derivative of x to the fifth power. Obviously, just using the power rule is way more efficient than going through all of these steps. That's not the point of this. This is to verify that the product rule is doing what it's supposed to do. Okay, so you would never use the product rule in an example like this one, but you would use it in examples like this type of function up here where you have no other choice. Okay, so let's give a few examples a try. I have three functions here. I want to take the derivative of each one. Now this first function, y equals 4x to the fifth, 4x squared plus 5 times 3x to the fifth minus x. We can take the derivative of this without the product rule. We saw examples similar to this one in the previous section. The technique you could use is you could multiply this out and just see the polynomial completely expanded out and then differentiate that using all of the different rules we talked about in the previous section. But the product rule allows me to take a derivative of this thing without having to do any preliminary algebraic steps like multiplying it out. So what would that look like? Well, what I'm going to do is I'm going to decide which function I'm calling u and which one I'm calling v. So I'm going to call this first set of parentheses u, the second one is going to be v, and I'm going to identify what u prime and v prime are. So u prime is the derivative of 4x squared plus 5. The 5 is a constant, its derivative goes to 0, so we know that that kind of goes away. 4x squared, I would use my power rule. The 2 comes down, multiplies to the 4, which gives me 8x, and then I subtract 1 from the exponent, giving me a 1, and I don't even really write the 1. I just write it as x. That's u prime. What is v prime? Well, v prime is the derivative of this set of parentheses. 5 comes down, multiplies to the 3, makes a 15, and then I have x to the fourth, subtracted 1 from that exponent. X, we know its derivative is just 1, so I have 15x to the fourth minus 1. All right, now I'm not going to write this every time, but for this first example, I'm going to rewrite the statement of the product rule. So it's the one that says this: if I want the derivative of uv, which again is the same thing as what I'm trying to do up here, I'm finding y prime, which is the derivative of uv, then it's equal to u v prime plus v u prime. Okay, so now I'm going to take the different functions that I know that all of these are equal to, plug them in. U is this function here, 4x squared plus 5, and then I'm multiplying that to v prime, which is 15x to the fourth minus 1. And then I'm going to add to that v times u prime. And, you know, whether you write this as v u prime or u prime v, those are going to be the same thing. Multiplication has what we call the commutative property, which means you can switch the order of the things you're multiplying and you get the same answer. The reason I'm saying that is because I actually would like to put u prime first. I'll explain why in a second, but u prime is 8x, v is 3x to the 5th minus x. Okay? Now, the reason I did that is because typically, if you are multiplying two things, and if one of those things is just a single term, like an 8x or like an e to the x, or just like a single term like this, and the other thing is something that has more than one term, so it's going in parentheses, math people like to put the single term thing all the way to the left. It's just a visual thing. It's not wrong to put 8x over here, but it's just we like it a little bit more when it's over here. So that's why I switched the order of multiplication there. At this step, I would actually just say that I'm done. Depending on what I'm using this derivative for, it might be desirable to multiply everything out and then maybe refactor it. But because we're only asked for the derivative, we have done that, even if it's not in the simplest possible form. I'm going to be fine just keeping it that way. Okay? All right, so let's look at another example. F of x equals x squared e to the x. I'm going to set u equal to the x squared and v equal to the e to the x, which means u prime is 2x and v prime is e to the x. Remember, e to the x is its own derivative. Okay. At this step, I want to find the derivative, and like I said, I'm not going to rewrite the product rule every time I do one of these. I just wanted to do that in the first example. So now I'm going to go straight to what the derivative is. F prime of x is equal to uv prime, so that's x squared times e to the x, plus v u prime. So v is e to the x, u prime is 2x. And again, I'm actually going to put the u prime first. This is really just a matter of what kind of a convention that mathematicians tend to follow. We tend to, when we have multiple things that are all getting multiplied together, we tend to put constants all the way to the left, followed by anything that's like a polynomial. So x, you can think of that as a polynomial. And then after that, we will write things like radicals or exponential functions or logarithms. We tend to put those sorts of things further to the right. So this is just convention. It would not be wrong to say 2x over here. It's just not how we're used to seeing it. All right, that was a pretty quick one. That's all we had to do. Last problem. G of x equals the square root of x times the natural log of x minus 2 to the power of x. So this function has a product in it, but it's not that the whole thing is a product. I have a product of two functions here minus an exponential function over here. So if I first look at this as a difference of two functions, its derivative will be the difference of the derivatives of these two functions. So I need the derivative of root x natural log of x. Then I'm going to subtract from that the derivative of 2 to the x. But in the process of finding the derivative of this first piece, this square root of x times the natural log of x, that's where I would need the product rule. So it's not uncommon for the product rule to be just a step in finding a derivative and not the whole thing like the last two examples were. So what I'm going to do is set u equal to the square root of x. I'm going to set the natural log of x equal to v. And then I'm going to find those derivatives. Now we have found the square root of x, its derivative before. U prime, in a previous section, we showed that this is equal to 1 over 2 root x. You shouldn't just memorize that. You should be able to show how we got from here to here. And again, if you don't remember, the trick is to rewrite any radical function that you're taking a derivative of as x, or whatever the radicand is, to a rational exponent. So you can write x, the square root of x, as x to the 1/2 power, and then use the power rule on that, and then convert back into radical form, which is what I did here. So u prime is equal to 1 over 2 root x. V prime is 1 over x. That's what the natural log of x's derivative is. So when I find g prime of x, I have to find the derivative of this product, which is going to use the product rule. That's u times v prime. So that's the square root of x times 1 over x. Square root of x times 1 over x. Okay? And then plus vu prime. So that's going to look like the natural log of x times 1 over 2 root x. And then finally right here, minus 2 to the power of x. That is separate from our product rule because it's not part of this product. So we just take its derivative as you normally would, natural log of 2 times 2 to the x. That's the whole thing. It might be desirable here to get common, or to simplify this a little bit. So in this example, I will simplify just so we can kind of practice that a little. Square root of x times 1 over x is 1 over the square root of x. That's how that would simplify. And again, it's helpful to convert to rational exponents first and then use some exponent properties to get here. This becomes the natural log of x over 2 root x. And then this is just what it is, minus natural log of 2 to the x. I could leave it in this form, but I'm looking at my two rational expressions here, and I see that the denominators are so close to being the same. It's hard for me to leave it in this form. I'd like to add that into a single rational expression. So to get a common denominator, I have a 2 root x here. I would need to multiply this numerator and denominator by 2 to get a 2 root x there. That would put a 2 in the numerator here, so when I add those, I get 2 plus the natural log of x over 2 root x. And here, nothing has changed with this last part of our derivative. So in this one, did I need to do all that simplification? No, because I'm only being asked for a derivative. As you're going to see later on, though, specifically in chapter 3, when we start looking at some applications of the derivative, finding the derivative of a function is only the first step in the process that we'll go through in those chapter 3 topics. Then there's going to be more stuff that happens after that. Oftentimes what we're doing is we're taking our derivative, whatever it is, and we're setting it equal to 0 and then solving it. And we'll explain in chapter 3 why that's something that we're going to do a lot of. So when you're solving an equation that's set equal to 0, you often want to factor that and simplify it as much as possible because that helps you solve that equation. So we will get to a point where we tend to do more simplification of our derivatives like this. But I think throughout this section, I am going to kind of bounce back and forth between just leaving a derivative all expanded out like this and then occasionally doing some simplifying. Okay. All right. The next thing is the quotient rule. I'm actually going to start the next video with the quotient rule. So let's end this one here.